Good evening, Math 101 from Hazleton. Justin Pashara here once again. I apologize, as I said in the email, I recorded this lecture earlier today, and for some reason the video got corrupted. It could not upload after I waited all day for it to upload, so this is take two. So maybe this video will be better than the first one, who knows. I don't know about you, but I'm tired of staying in the house. And I mean, thank God I'm healthy and everything. Believe me, I'm blessed that I'm healthy and not sick. But between the dreary weather, I'm looking right out this window here, dreary weather, my grass it's like a jungle out front. I'm trying to cut it, it's wet, can't cut it. This coronavirus situation, I just want to get back to normal life, I think, like you guys do. Look at my hair is getting real long. I look like a beatnik pretty soon, you know. But anyway, the good news, at least, is that 6.3 is the last section for Math 101. So that's our last section that we have to cover. We covered a lot of ground this year, and I'm very happy with the ground we covered, especially during this pandemic, being at home, you know, doing this. It's not easy, so don't kid yourself. But I have to say, the vast majority of you in the class really handled yourselves well. Did the assignments on time. I mean, this is great. I couldn't have asked for anything better. I was kind of dreading this, kind of like with my high school situation. But being that you guys are adults, I think you can handle it a little bit better. And like I said, I'm very pleased. Very pleased. You know, I'm fortunate to have a class like all of you that are in it, because that makes a difference as well. But I'm very thankful that we got to this point. And we're almost there. We just have a little bit more to go. So this is section 6.3, rational numbers and decimal representation. So what I'm going to be talking about tonight here is just the basic things you need to know. And what's nice is this section is devoted just to the set Q. So if you remember, Q is the set of rational numbers. This is the set of all x, such that x looks like this. It looks like a over b, and a and b come from the integers, and b can't be 0. We can't divide by 0, so we have to put that restriction in up there. So in other words, this set is constructed by taking all of the integers and making quotients out of them. That's the best way to put it. And we're going to look at this set from two perspectives: the fractions that we readily see by definition, and the decimals that they represent. Because, for example, 1/2 is 0.5, 1/3 is 0.3 repeating. So we're going to talk about the decimal representations that they have. So the first thing we're going to mention here is that Q is dense. So we've seen this term dense before. Dense in this sense, meaning that on the set of rational numbers, between any two rational numbers, you could always find another one. So we could say if R and T are in Q, then we could say that there's another rational number S that is strictly between R and T. So for example, if we look at 1/2 and 1, we could certainly find another number in there that's between 1/2 and 1, for example. You could think in your mind of some numbers we have. Probably what comes to mind is like 3/4. 3/4 is between 1/2 and 1, because this would be 0.75, this is 0.5, and that's 1.0. It also goes the other way. We could look between 0 and 1/2. For example, we could put a 1/4 in between. A 1/4 is clearly in between 0 and 1/2, and you could do this process forever. So that's why Q is dense. You could always find another rational number between any two rationals. You can't say that about the other sets. For example, N on the natural numbers is not dense, because if you look between, say, maybe 1 and 4, you could say, okay, well, certainly 2 is between 1 and 4, which is correct. But how about if we pick between 1 and 2? Is there another natural number between 1 and 2? And the answer is no. So that set isn't as special as Q. We know that we can reduce fractions, and we can also figure out which fraction is bigger. So here's a trick for doing that. So let's say I have the fraction 7/8 and 5/9, and I want to figure out which fraction is bigger. Well, we could do a cross multiplication trick to figure it out. for example, in this case, 8 times 5 will give you 40, so I'll put the 40 up here. 9 times 7 is 63. What number is bigger, 63 or 40? Well, 63 is. So that means this fraction, 7/8, is larger than 5/9. And this is a perfect example to look at because oftentimes a lot of students think of it this way. Whatever number on the bottom is bigger, that's the bigger fraction. That's not necessarily true. Exactly like in this case. 9 is bigger than 8, but yet 7/8 is bigger than 5/9. So you can't use that argument. In fact, years ago, a true story, I think this was like 2003 maybe, or 2005, but the fast food chain A&W, they advertised a new hamburger, and they claimed that their hamburger was a half-pound burger, so that's pretty damn good if you like hamburgers. But yet, their leading competitors, they still offered their 1/3 pound hamburger. And guess what? Because people saw the 3, they thought that a 1/3 pound burger was actually thicker than a half-pound burger. So that's where your math judgment has to come into play. So believe it or not, A&W lost sales over fractions, if you want to believe that. It's kind of crazy, but it's absolutely true though. So that's the case there. So the cross multiplication trick will help you out to tell you which fraction is bigger. Okay, so that's something you'll see in your exercises. The next thing we're going to talk about is adding and subtracting fractions. This is something nobody likes, especially if you don't have a calculator. Now, when I was in school, I remember learning to make a list of common denominators, and we always wanted to pick the least common denominator. Well, you don't necessarily have to do that. There's another way you can do it. I'll show you here. And while sometimes it doesn't give us the least common denominator, it's a time-tested, proven fact that will always work, no matter what two fractions you're given. So let's start off with a classic example that I always usually pose in high school too. I want to add 1/2 and 1/3 together. And you could probably guess in most of my classes, if I ask that, someone will say, oh, that's 2/5. Well, if it was a perfect utopian world, Mr. Pashara, it would be 2/5, but it's not. So in order to add fractions that have different denominators, we need to get a common denominator. So here's how the formula works. This formula from long ago, from time-tested mathematicians, say if you have a fraction like a over b, and you want to add a fraction like c over d, you multiply the denominators together, and that gives you your common denominator. And then essentially you cross-multiply to even up your numerators. So it's going to be AD plus CB. In other words, the two numbers that make up your denominator form what we call product. So you have two factors, b and d, they make a product bd. So factor A, this factor of A here has the factor of b but not d. So we multiply A by d. And then this factor of C has a factor of d but it doesn't have the b. So we have to multiply it by b. Hence, as a shortcut, that's totally not proper, however to say, you could cross multiply to even out the tops. So, with that being said, if I have 1/2 and 1/3, I multiply the bottom, so 2 times 3 is 6. That's our common denominator. Now this 1 has a factor of 2 but not 3, so I'm going to multiply 1 by 3, plus this 1 has a factor of 3 but not 2, so it's going to be 1 times 2. And that, my friends, is the hardest part of it, because now we just do the arithmetic. 1 times 3 is 3. 1 times 2 is 2, 3 plus 2 is 5. So your answer is 5/6. Just like that. Okay? That's how you do it. It's probably easier than what you learned when you're in elementary school. Now, I think this is easier than what I learned. Let me give you another example. How about we have 4/9 take away 5/8. So the rule applies when you subtract too. And it applies for signed fractions too, like if you have a negative rational number like -4/9 or -13/3, it still works as well too. So let's test out this formula here essentially. feel like I'm getting bit by a bug or something. I don't know what the hell. All right. So look at your denominators. You have 9 and 8, so multiply them. 9 times 8 is 72. This 4 has a factor of 9 but not 8, so we're going to do 4 times 8 minus 5 has a factor of 8 but not 9, so it's going to be 5 times 9. 8 times 4 is 32 minus 5 times 9, which is 45 over 72. And then when you subtract, you have 32 minus 45, that's going to be negative 13. So your final answer here is negative 13 over 72. Easy as that. Not much to do, right? Now, here's the only thing that could be a drawback from using this method is, as you can see, the denominators sometimes get rather large. So you may have to go back and reduce the fraction sometimes. It doesn't happen here. You can't reduce 13 over 72. However, you may get a situation like 5 over 10 or like 20 over 40 where you do have to go back and reduce. But I think at this point you're all capable of doing that. Let me give you another example that you may see. We may, a fraction, by the way, a fraction that has a bigger top than bottom. So let's say 13 over 3. This is what we call an improper fraction. An improper fraction. But when you write something like 6.5, we call this a mixed number. So those are probably familiar terms from back in elementary school. Now sometimes you may have to add or subtract mixed numbers, which isn't too bad. I'll show you how you would do that. Let me erase some of this other stuff. If you have to add or subtract, or really actually multiply or divide mixed numbers, the method's kind of the same. Your first step is to turn them into improper fractions. So say we have 6.5 plus, let's say, 7 1/3. And we want to add those two things together. You've got to turn both of them into the improper fractions that they represent. So 6.5, that's going to be 13 over 2, because 2 times 6 is 12, but add 1 is 13. So you got 13 over 2 plus 7 1/3. 3 times 7 is 21, plus 1 more is 22. So that's 22 thirds. So now the problem is reduced to 13 halves plus 22 thirds. So we just have to go ahead and find our common denominator, like in the last example here. So multiply the bottoms. 2 times 3 is 6. 13 has a factor of 2, but doesn't have the factor of 3. So we're going to do 13 times 3 plus 22 times. 22 has a factor of 3, but not 2. So we're going to multiply it by 2. So 13 times 3, I think that's going to be 39. Plus 22 times 2 is 44 over 6. So let's see, what is 39 and 44? 9, 10, 12, 13. Looks like 83. 83 over 6. Can we reduce 83 over 6? Our only shot, I think, here is going to be 3. So let's just check it out. That goes in 2 times. Nope. So this is as good as it's going to get. So our final answer is 83 over 6, and that's an improper fraction. Okay? So that's how you do that type of thing. Now, if we want to multiply two fractions, it's a little bit different. It's a little bit easier. So if we want to multiply two fractions together, say we have 1/2 times 1/3. All we have to do here is multiply across the top and multiply across the bottom. 1 times 1 is 1. 2 times 3 is 6. Your answer is 1/6. You're done. If only adding and subtracting was that easy, right? And it works when we have sign in numbers too. So maybe like -5/6 times 1/3. -5 times 1 is -5. 6 times 3 is 18, negative 5/18. Easy, right? Now, by the way, whenever you have a fraction that has a minus with it, you can write it in 3 different ways. They mean the same thing. So you can put the negative up on top, you can put the negative on the bottom, or you can put it smack dab in the middle. All 3 of those things right there, guys, represent the same thing. So don't let it fool you. If you ever written one of those 3 ways, they all are equivalent. Negative in the top, bottom, or in between. And lastly, in terms of operations, we can look at dividing. Now, dividing is a little bit more odd, but it goes back to something I told you a long time ago. That in mathematics, there's really only 2 true operations, really, with addition and multiplication. Multiplication and addition. What that means is when you divide fractions, you are actually multiplying by a reciprocal. So, what the rule would say here is, if we have a over b times c over d, what this means is a over b, this should be a division sign, I apologize, a over b divided by c over d. That's the same thing as saying a over b times d over c. In other words, a division problem becomes multiplication, and then that second fraction we flip it upside down. That's called the reciprocal, okay? So, for example, let's take this problem here. If we have 1/2 times 1/3, and we make it a division problem, and say 1/2 divided by 1/3, what we're going to do is we're going to say 1/2 times the reciprocal of 1/3, which is 3 over 1. You see? So 1/2 times 3 over 1, that's your new problem. And we just go ahead and do that. It's going to be 3/2, just like that. Let's say we have negative 8/3 divided by negative 5/4. So it's going to be negative 8/3 times negative 4/5, which would be positive 32 over 15. And that's how you would do it. So division becomes multiplication, and then you flip-flop the second fraction, and then multiply, and you got it. Okay? So this is probably a good place to pause. Maybe if you want to look over some of your homework exercises on adding, subtracting, multiplying, dividing, see if you can do a couple. The next part here is we're going to now look at the decimals, their representation of the fractions. And then one cool thing, well, I think is kind of cool anyway, that you may not know how to do. How do we write a repeating decimal as a fraction? Okay, that's kind of interesting. We want to get it exact. We don't want to make an approximation. So we'll take a little break here, pause, see what you can do, and I'll come back and show you some more stuff. Okay. So next we're going to look at our set of rationals, of course. But now we can think of these in terms of decimals. So rational numbers are either terminating decimals or repeating decimals. So terminating decimals you're very familiar with. For example, 1/2 is written as 0.5. It's terminating because the decimal stops after one spot. Something like 3/8, for example, 0.375. That would be considered a terminating decimal. It stops after 3 places. Negative 89 over 100 would be negative 0.089. Again, the decimal stops after a finite number of places, okay? So, that's terminating. Now we want to look at repeating. Now we know some of these. For example, 1/3 is 0.3 repeating. We put that little bar over top of the 3 to tell you that that 3 spot goes on forever. 2/3, for example, is 0.6 repeating. Now, what's interesting about this is, if you go in your calculator and do 2 divided by 3, it's going to say 0.666. It's going to fill up all these 6's, but then in the last spot, they're going to give you a 7. And then they're going to trick you to think, oh, this means 0.67, but it doesn't. That's just the way the calculator does it to show you that's kind of rounding up that last spot. But exactly 2/3 is 0.6 repeating. Another example would be something like 5/6, which is 0.83 repeating, but only the 3 spot repeats. So only the 3 goes on forever, not the 8. So with that being said, we're going to do something interesting here, which is take a repeating decimal, one of these guys, and write it as the fraction it represents. See, it's easy to go from fraction to decimal, but not decimal to fraction. Okay, so this is, I don't want to say this is hard. You need to know a tiny little bit of algebra, like this much, right? If you never had algebra, you're still going to survive this, no problem. Well, let me show you. So what we want to do is, this is the directions will be. I'm going to say, right, 0.85 repeating as a quotient of integers. Quotient of integers is a fancy way of saying fraction, okay? That's the way the PhDs like to say it. They like to be sophisticated, you know. We don't want to say fraction, let's say quotient of integer, makes it sound a little more intellectual. Nonetheless, what we're going to do here is an interesting task. We're going to take this 0.85 repeating, and we're going to write it as a fraction, an exact fraction, no approximation. So I have this in your notes for you, step by step. You'll see it live here in a problem. Your first step is we're going to assign a variable to represent what this number looks like. So I'm going to say let x equal 0.858585 ... And you can put in as many 8.5s as you want, and then make sure you put the 3 dots at the end to tell the reader that that number goes on forever. So that's your first step. Now my next step is going to be this. Look back at that number. How many decimal spots repeat? In other words, does 1 digit repeat? Does 2 digits repeat? Does 3? 2 digits repeat. So we multiply in terms of powers of 10. 10 and 10. 10 times 10 is 100. So what we're going to do is multiply this equation on both sides by 100. So we take the x and multiply it by 100, you get 100x. That's your little bit of algebra. Equals, when you multiply this by 100, it moves the decimal 2 to the right. So that means we're going to have 85.8585 ... So I multiply both sides by 100 because 2 spots repeat in the problem. What I'm going to do next now is take the original equation and subtract it from this new one. So I'm going to put minus x equals, and carefully line up the 0.8585 ... like that. Okay? Not so bad. Now there's an interesting thing in mathematics. It's called telescopic cancellation. And what it means is, in theory, when all of these same digits repeat forever and we line them up, we could actually cancel them out if we were going to subtract them, right? Like if you had 85 minus 85, that's 0. All the digits line up they subtract to be 0 each. So in theory, when all these digits repeat, we're actually able to cancel all these out, right? All of them out. So that 5, those 8s, the 5s, the 8s. But when we get here, we can't cancel out because 5 doesn't cancel with 0. So over here, you're going to have just left the 85. And here, 100x minus an x. And if you're new to algebra, if there is no number in front of x, we assume it to be 1. So it's like saying 100x minus 1x. And that would give you 99 x's. Imagine if you had 99 x significant others. Boy, that would be rough. Whew. I'm nowhere near that. Okay, so now we have 99x equals 85. And now what we want to do is, again, if you're new to algebra, we don't want 99x, we just want x. So what we do here is divide both sides by 99. So what we have left is x equals 85 over 99. And that, my friends, is your final answer. 85 over 99 is the fractional representation of 0.85 repeating. It's kind of cool, isn't it? That's how it works. Okay, so I'll stand back and let you absorb that. We'll do one more example where only one digit repeats because you have a little bit of extra work to do, but it still follows the same pattern. Okay, so we're going to slightly modify this, and I'm going to write this as 0.85 with a repeating 5. So only the 5 is going to repeat this time, okay? And let's see how that alters the problem just a little bit. So my first step, if we have 0.85 and a repeating 5, we're going to say let x equals 0.85555 ... So only the 5s repeat this time, okay? Now, how many spots repeat? Well, only 1. So that means we're only going to multiply by 10 this time and not 100. So we're going to have 10x equals 8.5555 ... It only moves the decimal over 1 to the right. We take the old equation and subtract it from the new one, so it's minus x equals 0.8555 ... Again, carefully making sure you're lining up the decimals. You don't want them to be out of whack. 10x minus x is 9x, so that's on the left side. Now, here's what's a little bit interesting on the right. Again, we have all these continuing decimals, so we could be canceling all these out. The 5s cancel with the 5s, the 5s cancel with the 5s, 5 cancels with the 5. 5 does not cancel with the 8. So when you get to here, this time you have to do the actual subtraction of 8.5 minus a 0.8, which is 7.7. Okay? So that's the only new thing. We end up with a decimal here. We have to get rid of the 9, so we'll divide both sides by 9. So what we have left here is x equals 7.7 over 9. And you may be thinking, all right, Pashar, we're done. Hip hip hooray, let's move on to something else. Not quite, because the direction says quotient of integers. 7.7 is not an integer now, is it? It's a rational number, but it's not an integer. So we got to make the 7.7 an integer. And the way that we do that is we'll move the decimal over 1 to the right and make that a 77. If we do that to the top, we've got to do it to the bottom to balance it out. So we'll move the decimal over 1 here, and that's going to make it 90. Now we're done. So 77 over 90 is your exact fractional representation of 0.85 repeating with a repeating 5. I think this is kind of cool because even if you're not good at algebra or you've never done algebra for that matter, there's really not a lot involved here. It's very procedural, okay? So I hope these two examples help you. If you can do these two, I think what's in the textbook you'll be fine with. It brings us to an interesting point that a true fact is if we have 0.9 with the repeating 9, that's actually equal to the number 1. Now you're thinking, how the hell can that be? 0.9 repeating is actually the number 1. It is. Indeed it is. And if you go through this procedure, you'll prove it to yourself. And that's something I encourage you to do, is to go back and show that fact, to prove to yourself that, my God, 0.9 repeating is actually the number 1. Our buddy Cantor, that we talked about in the set theory chapter, he had much to do with this infinite decimal type stuff. Okay, so with that being said, that puts a close on section 6.3, which is actually the very last section that we're going to do in 101 this semester. So again, I applaud you guys to getting this far. You only have one more homework assignment, which is this one. You have one more quiz coming up to do, and that's due on Thursday, which is the older stuff. And on May 1st, okay, so May 1st, I will be releasing the final exam on Blackboard. So on May 1st, you'll be able to see the final exam, and you'll submit it just like you've done all the other ones, okay? Just take a picture of it to me. And if you could, make sure you hold if you're doing your cell phone, hold your cell phone up long with it. Don't go sideways. Take the picture up and down. This way, if you're attaching an email, it's a little bit easier for me to read. But for overall, most of you have been sending very good pictures. I can't complain. I can read everything very, very well. Some of you have been using like a scan app off of your Android or iPhone. That works really well. But just keep doing what you've been doing. The way you've been submitting the work is excellent. I have no problems with it. You can even text me the work if you need to at my phone number as well. So until next time, this is really the last lecture video other than before the final exam, which will be due on May 14th, by the way. That'll be the cutoff date. So it'll be released on May 1st, but it'll be due on May 14th, okay? I'll be open to doing review sessions from my house here. So if there's any topics you want me to go over, because I do have the study guide on Blackboard as well for the exam. If there's any examples you want me to do, just send me an email, give me a call, send me a text, and I'll put a video together with some of those concerns, and you'll have some extra problems to look at while you study. So until next time, my friends, stay safe, stay sane, and enjoy the rest of your Sunday evening. Thank you.